Good afternoon, this is Mr. Schweitzer, and this is a video kind of highlighting effusion and diffusion, and we'll also look at implications of kinetic molecular theory. We'll also include things of average kinetic energy and also molecular speed, velocity, and a few other little small things. So now, let's say, for example, we have two balloons. Now, a balloon, let's go balloon A, which let's say has helium in it, and let's go balloon B, which has, let's say, oxygen in it, O2. And I eventually want to talk about effusion, diffusion, but in this case, we will be highlighting a few other things along the way. So these two balloons are the same size. Let's even say they're 2.4 liter balloons, 2.4 liter balloons. They are at, let's say, STP, so 1 atmosphere, and this is the temperature of 0 degrees Celsius, 273 Kelvin. Alright, so now in this case, because they have the same volume, they have the same temperature, same pressure. Remember, the pressure on the inside equals the pressure on the outside, because if the pressure inside was bigger than the outside, it would literally expand. At this point, a couple things we could figure out about this balloon is one, PV equals nRT, and I'm looking at number of particles, N equals PV over RT. They have the same pressure, same volume, same temperature, same constant, so technically N is equal between the two. Total number of particles are equal. Alright, what else do we know about this thing? Well, they have the same temperature, so they have the same, what we call, average kinetic energy. Another thing for average kinetic energy is temperature. Now, this means that sometimes we have particles that are traveling very fast. Okay, some particles traveling a little slower, but based on their mass and their total energy, the average is the temperature. So this is kinetic energy, of course, average equals 1/2 mass velocity squared. So each of these has their own 1/2 mass velocity squared. Give myself a little room here. And 1/2. Come on. Come on. Losing my eraser here apparently. Okay, pen is back. Alright, so we have in this case 1/2 mass velocity squared, 1/2 mass velocity squared, and because they have the same kinetic energy, then in this case a faster moving particle must have a smaller mass. So smaller mass, higher velocity. This guy's got the higher mass, so it's got a slower velocity. So all of these guys are flying around inside here and hitting walls, producing pressure. But the helium is hitting at a greater rate. These particles are traveling faster, having more collisions with the wall. Now the collisions aren't as violent because they're not as massive, but together, more collisions that are less violent equal less collisions of a greater violence, greater energy. Okay, so, or shall I say greater force. Alright, so now let's take a moment and let's highlight this idea of average, just so you're aware what it means by average. In all the particles present here, we have this graph that can be sort of described as Maxwell's distribution. The name isn't as important, but they would show that the speed of particles might look like this. And this would be sort of energy, or it could be movement. This here would be number of particles per energy. So when I multiply these two things together, area under the curve is just going to be total number of particles. So in this case, quite often we might see a problem around this thing where it's okay, well, what happens if we warmed these particles? They start moving faster. Again, this is a little off note, but we just stick it in right here. If I warm this thing, there's a few things you want to note about this thing. One, the total number of particles will not change. The area in the curve must remain constant. Okay, and there's always going to be some particles that don't have any movement. So if I want to draw this curve to match a warmer, one, I must go to the right, and two, I must maintain this zero connection, and three, I must maintain the area of the curve. So I might do something like this, where again the area under the curve is the same. This is my average right here at the higher temperature. So a couple things, and the curve is maintained starting at 0, and I have a higher average. So that's like warming it up. You'll see occasional problem like that. Now let's go back to the actual topic here, is this idea of effusion versus diffusion. And in a balloon, what you want to note is that even though you can't see it, there are small little holes in these balloons. And I can just put a hole right here, hole here, hole here. As the particles fly around, hitting walls, bouncing off, they occasionally, by random chance, hit a hole and squirt out. This is effusion. So effusion is different than diffusion. We'll show that in a moment. But helium, because the same balloon has the same holes, they hit the walls at a greater rate. Therefore, they have a better opportunity to hit a hole. Not because there's more of them, or not because they're heavier, because they hit the walls at a greater rate. They have a higher molecular velocity. So even though these two things have the same exact temperature, this helium has a greater molecular velocity because it's less. For the same given energy, it's got a higher velocity. Okay, so now at this point, what do we know about this? Well, this guy will hit the holes faster, therefore the helium will escape. You might notice this as a kid. You go and you have a balloon, and the next day the helium balloon is essentially deflated quite fast. Yet a regular balloon might last 2 or 3 days longer. So we have picture of this, I guess, effusion versus diffusion. Diffusion would be simply like putting something into a beaker, and particles are escaping from this thing, and over time the particles just escape into the area, going from areas of high to areas of low by random motion of particles called Brownian motion. I thought that's important. Effusion, so this is diffusion. Effusion, alright, is if I were to take that same scenario technically and produce a cover on this thing which had some holes in it. And now it needs to make it through not just the open area, but needs to make it through some of these holes. Anytime we're escaping through a hole, we call effusion. So the same item, particles bouncing around, and eventually they squirt out a hole. Mathematically, the math is the same. It's called Graham's law of effusion diffusion. Rate at which one item effuses over the rate at which a second item effuses equal to the square root molar mass of the second guy over molar mass of one. Now we can go back to our original example where we're talking about what do we have here? We had helium versus oxygen. Okay, well, in this case, this number is generally cited as one item. So we know that the helium balloon will effuse faster than the oxygen balloon. This guy has a molar mass of 4. This guy's got a molar mass of 32. So technically, the oxygen is 32, not 36. The oxygen is 8 times heavier. That doesn't mean that it is 8 times as fast. Okay, so I want to know how much faster is the helium going to be than the oxygen. So I'm going to make rate 1 equal to the helium, and then the rate 2 is going to be the oxygen. And this number is going to be into one item, one number. It's going to be a ratio of helium to oxygen. And it's going to be one value. So it's that number per one oxygen. How many times is helium effused versus the one oxygen? And therefore, just we plug it in, molar mass of oxygen is the 2. Okay, so that'd be 32 divided by, in this case, 4. Gives me the square root of 8. In your head, you might know that 2 times 2 is 4, 3 times 3 is 9, so someplace between 2 and 3, and it ends up being closer to 3, which is equals 2.8. So oxygen or helium effuses 2.8 times faster than does the oxygen. Now, if I reverse this, I would get a number less than 1, and that would be this, the times that oxygen effuses faster than helium, again, is smaller than 1. 1 divided by 2.8 would be your answer. A couple topics here again that we reviewed. These are going to be effusion, diffusion. Kinetic molecular theory is any time you're looking at a gas particle at the molecular level, traveling fast, traveling slow, how they're bouncing off walls, how they act as a particle. Lots of kinetic molecular theory here. Average kinetic energy, molecular velocities, how we get our average, very important. Effusion versus diffusion, right here, and of course the calculation of these guys, very important.